Thumbs up. Okay, excellent. All right, I guess we'll just get started. So welcome everybody to HotPETs 2021, brought to you from a pixelated Rochester. Hopefully you've all had a chance to explore pixelated Rochester. I now know 1,000 times more about Rochester than I ever did, even though I spent my youth watching Rochester's Fox station, including their news, because that just happened to be what was broadcast to my house if you wanted to watch The Simpsons. So we have a really nice program set up for you this year. There's going to be 2 sessions, 3 talks per session. The talks are each 15 minutes, and then we've got a 30-minute block at the end of each session carved out for a discussion. As I just mentioned, for those of you that didn't hear me, the discussion is more of a proper discussion than a Q&A. We encourage you to bring your own ideas. We encourage the speakers to pose questions. We encourage lively debate, joking around, etc. It's not formal like the conference question and answer period. So if you have anything even remotely intelligent to say on the subjects that were talked about, it doesn't have to be directly related to what the speakers said. Please, 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 let's all engage and keep this lively. So in our first session, we've got these 3 speakers that you can see in front of you: Mona Wong, Mohammed Malik Zeta, and Shubham Jain. After that, we will have a coffee break. Unfortunately, we can't provide the coffee. That's usually my favorite part of conferences, but we'll give you a chance to go brew some of your own. And then we have a very exciting keynote lined up. Merritt Hansen, a regular at PETS, is going to be talking about pets and data protection authorities. What is the A's? Yeah. Perfect is the enemy of the good, talking about the interplay between regulation and regulators and the sorts of technologies that we all spend our days obsessing about. And then we'll have another short break, followed by the 3rd session, or the 2nd session, the last session of the day, which has got 3 more talks, same basic idea as the first session. And then in the regular HotPETs tradition, we are going to have a vote for the best talk. So we'll be using this Menti website. We'll provide this information again when it's actually time, but you enter this code, you give your vote, and whichever talk gets the most votes will win a prize. And so we'll discuss that with the presenter after. Because of the virtual nature of this, we have to send the prize to the presenter, so there will be a bit of a delay. But be prepared to vote for your favorite by whatever criteria you deem fit. And then we will all convene. You may have noticed the very bottom of Gathertown, there is an ice cream bar. Again, much like the coffee, this year you're forced to bring your own ice cream. Hopefully you've all got some stashed away in your freezer. And we'll hang around and eat ice cream and continue to talk pets or whatever we feel like talking about. So with that, I will hand the floor over to our first speaker, Mona.
Okay, hi. I will start presenting. One sec. All right, great. Thank you for that introduction, Ryan. That was great. Hi, everybody. I'm Mona. I'm a graduate student at Princeton University, and thank you to HotPETs for having me. I'm excited to be here. I'm sorry for the mess in the background. I'm moving right now, but I'm excited to be presenting here instead of packing. So today I'm going to be talking about leveraging connection migration for network privacy, also known as COMPS, my very cool and very legitimate backronym. So let's talk about pets. I love privacy-enhancing technologies. I love animals. My parents were unfortunately allergic, so I never had pets growing up. It was because of that in my youth, I was severely addicted to a gaming website called HotPETs that lets you care for virtual pets and play games with them. Unfortunately, my legal adult guardian, depicted here by this disembodied eyeball emoji, thought my addiction to Neopets and the internet in general was morally objectionable which like maybe, and also bad for my developmental health, which is probably very true. And so as many of you probably already know, there are lots of ways. Unfortunately, your regular internet usage is not at all private. It will reveal what you're doing to anyone on the network listening, for instance, the parent that runs your home router. So unfortunately, it was quite easy to put parental controls on the router and foil my gaming experience and also my youth. So whenever I got blocked, I would be very sad because I could not feed my fairy cow. So I did what any desperate 8-year-old would do in the early 2000s, which was to ask my friend Jeeves about it. Luckily, Jeeves actually had great advice. He told me to use VPN, use Tor, and armed with this new information and this new technology, I was able to feed my cow and freely surf the web, and it was glorious for this period of time. However, my legal adult guardian only got smarter. They realized that even if my connection was encrypted, it turns out the sizes and the timing schedule of packets is enough to fully identify the website I was visiting. So they memorized the general packet timing and sizes that the network would experience when I opened Neopets, and they would block the connection whenever it occurred. So it turns out that today, this is actually a whole subfield of CS network privacy research called website fingerprinting. So state-of-the-art web fingerprinting classifiers, nowadays are using complex neural networks to discriminate between hundreds of websites, like convolutional neural networks, and they even work well in the context where you experience unknown or not before seen traffic or websites. And even non-neural network classifiers work pretty well. There's K-fingerprinting, which uses manually engineered features with random decision forests. That works quite well. And so, like in the face of machine learning-driven network surveillance attacks, I was completely defeated by my legal adult guardian, and there's nothing I could do. So for now, we're going to elegantly segue into talking about modern encryption and network protocols. This is their site banner as of now, I think. I think this, this is a really smart move. Global smartphone penetration is almost 80%, and everyone has a phone. So in practice, what does this mean for me? Well, this just means that I'm going to be browsing Neopets on my mobile phone. These days, my phone and your phones probably also are real estate moguls. They have not one, often, but two network addresses on the internet, one through your Wi-Fi, one through your mobile provider. In the TCP-based internet, moving between network addresses is very annoying, right? When you walk outside your Wi-Fi range, your phone switches data, TCP connections have to get dropped and restarted on the new network because they're so tied to the network address. These kind of network changes also happen when you're not moving. If your mobile NAT just decides to change or rebind your phone's IP address. So luckily, many modern UDP-based encryption protocols are network agnostic. So, in other words, unlike TCP, which tightly couples connections to individual network addresses for many UDP-based encryption protocols, the connections are not defined by the address, but by some other data. So it's just the negotiated key pair or a proxy for it. The biggest one is QUIC, which was just made into an RFC. I think like maybe a couple months ago. I don't know. And is really rapidly gaining support. It's going to be the sole transport for HTTP3. It supports connection migration. There's also protocols like WireGuard and Mosh that both support IP roaming, as long as the received packet is valid, the server or the end will accept it. And so to be a little pedantic, this is what such a migration might look like, in particular for QUIC. At some point, our device will change the network. They'll detect the change network, maybe rebind, the socket onto the new, onto a new port, and then send data from the new network address. And so long as the server is confident that it comes from the same endpoint, it'll accept the data, even in the middle of a session. So one gotcha is that in QUIC, the protocol requires a two-way reachability to be established first. So there's this probe before accepting more data on a new network path. In practice, path validations can also be cached. We're going to talk more about the sort of practicalities of quick connection migration if you're interested in the discussion. But we've sort of established what connection migration is, I hope, at this point. So now let's talk about what COMPS is. What is COMPS? And so the primitive here, and the cool intuition is that we can split a session in the middle of a network connection. This breaks a lot of assumptions that network control devices currently rely very heavily on. Devices like parental control. So let's go back to our adversary who's using a machine learning to determine when I'm visiting Neopets. And using this insight, for the same individual connection I'm making to the Neopets homepage, I can send packets from different addresses. Supposing Neopets supports something like Quick, this would work. Some intuition as to why this might foil even advanced web fingerprinting defenses or attacks. Until recently, a lot of defenses against web fingerprinting often involve obfuscating the size and timing information by, injecting dummy packets or standardizing packet sizes. The COMPS kind of defense and other recent web fingerprinting defenses involve lowering the amount of actual information the adversary can learn. So now the adversary has more problems to solve, right? Beyond just what is the network fingerprint, and what are the possible ways they could slice it? How are they going to sample from the network fingerprint? And then they also have less information to determine what the network fingerprint is in the first place. So there's also a sort of combinatorial explosion of the slices. But what if I'm not multi-homed, right? A cool thing about COMPS is that I can utilize different encrypted protocols over the same network as long as the packets are delivered to the intended destination and also routed back accordingly. So here I'm showing 2 different VPNs, but we can imagine one of these is maybe just a regular encrypted quick transport or another encrypted proxy. It's up to you. It's your imagination. On the wire format, even if the adversary can see all the traffic, it can sort of make the correlation of the same flow more difficult. We also have the extra problem to solve. What are the ways the client could splice the connection here? I think intuitively this is maybe less strong than the previous one. But we can also combine the two, right? If this doesn't convince you. Not only are we using different paths, but also different protocols. And so on the wire, it might look something like this. We have different protocols being sent down different paths. You could also limit one protocol to a single path. It's up to you. And so one valid complaint or gripe might be, Neopets doesn't default to HTTPS yet. What makes you think they'll support Quick anytime soon? That's okay. Yeah, that's true. Like we mentioned before, we have other encrypted UDP protocols like WireGuard that also support IP roaming. So we can do all of the tricks that we mentioned in the past 5-6 slides. But instead of connecting directly to Neopets, we can just connect to a regular unaltered instance of WireGuard. And so here's a quick summary of all of the things we've learned so far. So with COMPS, we have this powerful primitive involving mid-sessions splitting. We can split across different network paths, different sort of encrypted protocols, as long as the packets get delivered to the endpoint, as long as the endpoint is, a connection migration endpoint. And there's minimal overhead. We can also talk about that in the discussion a bit as well. We don't really get into that here. That's pretty cool. And so I'm going to break up the talk a little bit because it's very early where I am. I don't know about you all. And with a little demo, it's nothing special. It's just going to show the connection migration. So we're going to be taking a look at sort of this model. And so what we'll see is we'll have TCP dump sort of listening on the 2 interfaces of the client, and then we'll run a very simple, packet scheduling on the client as well to split between the paths. And so it should just be able to remove this here. All right, and here, so we'll have here, I'll TCP dump here on the, well, let's do UDP only because sometimes, oh, what's going on? All right, and then TCP here on the 0 interface. Let's open a website on the client. You can sort of see I think something's gone wrong. Never do live demos, friends. Oh, this is capturing the VNC traffic. I'm sorry. There we go. refresh here, we can see all of the WireGuard traffic or VPN traffic going through ETH0. Nothing's going on. We can just run a really simple migrate script here, and this will basically just alternate interfaces 5 times a second. And then we run here, we can see the traffic just sort of bouncing between the two interfaces. Successfully visit neopets.com. It's gone mobile, and so have we, evidently. Okay, so that's it. That's the demo. All right. Let's go back here. Okay, I think I'm running a little low on time, so I'm going to sort of skip over the slide. Again, we can talk about it later as well. So another thing I want to point out that I think is very important is that comps also has other use cases, right? So we've been focusing primarily on the web fingerprinting threat model, defeating the sort of biblical angel that is managing my router. But let's consider a more common one. SNI censorship, is on the rise because HTTPS is on the rise, and I mentioned, when you connect to an HTTPS website, the server name is completely in the clear, and this makes a really great target for sensors, surveillors, etc., to use as a clear text signal to either block the connection or throttle it, or take some other action like throttling it. So you might ask, why don't we do the thing that our good friend Jeeves told us to do and just use a VPN, right? That worked last time. And so to that, I would say, VPNs maybe are too slow. I'm gaming here, so I clearly need that low ping to defeat my enemies and successfully play Neopets. And so comps enables a sort of compromise, right? Throw the handshake packet over the VPN path, then migrate the remainder of the connection back onto the sort of regular fast network path. And so if your adversary is just doing sort of keyword censorship, nothing complicated, then this would work. And I can continue my gaming career on Neopets. There are also probably other reasons other than gaming to desire a faster internet connection, but I'll leave that to your imagination. So in conclusion, some items, connections are less and less dependent on network addresses. That's very cool. So we're proposing comps to perform this sort of mid-session splitting as a general defense against web network controls in general. Some items we might flag for discussion that could benefit from all of your expertise and your thoughts. First is talking about systematic security evaluation. There's a sort of explosion of hyperparameters for a very flexible system like this. How do we design the best instantiation of comps given certain resource constraints? Can we quantify the limits of what an adversary can learn from certain slices of the traffic? We don't have a great answer for this other than sort of generating data sets with different comps instantiations and throwing dozens of hours of ML at it. And then, if the CNN doesn't work, then we're like, yay, this is probably secure. But this doesn't seem very systematic to me. And also, I strongly dislike running ML evaluation, so please help me. And the second one is other use cases. So we focused on web fingerprinting because there's this established academic narrative, and it's very interesting. But I've seen, tricks other than the one we talked about here that involve connection migration to do censorship circumvention. So we invite the community to continue to think about other threat models and how network agnostic protocols are sort of breaking the primitives that network control is reliant on. That's all I got for today. Can I unshare? Yes.
So thank you very much, Mona. Interesting talk. I'm sure that will generate lots of discussion, even if the discussion ends up centering around fond memories of playing video games. So our second speaker is Mohammed. Take it away, Mohammed.
Thank you very much. I hope you see my screen. Hi, everyone. Very happy to be here. I'm presenting our recent work with Anastasia and Denise on honest but curious nets. Basically, we show that sensitive attributes of private data can be encoded into the classifier's output. Let's start with a motivational example. We know that infinite information can be extracted from users' faces like crazy, attributes of emotion, how attractive we are, and even what is the body mass index just from face image. These are all attributes that you can find public data sets for them out there. And we know that every face has a face print. All mobile devices are using to identify people, but we are not always want to be identified everywhere. So we care about the sensitive attributes that about our private data are collected. As another motivational example, just a few weeks ago, an insurance company tweeted something which quickly went viral and led to a blog post by that company apologizing that this is not what people are understanding about what we are doing. But the point is that when an insurance company says that we can extract non-verbal cues from your face images to understand whether you are lying or not lying about a claim, people are showing sensitivity. And the point is that what are these non-verbal cues that you are extracting from my video to, for example, process my claim? So this shows that when we processing people's private data, we are not supposed to collect as much as we can. We sometimes just supposed to collect what we agreed already with the user to collect from. Let's consider this scenario that I have a private data, for example, is my face image. Here is Alan Turing, by the way. And the task is to predict the age, for example. And there is a machine learning service providing a model which is an age classifier, and it's supposed to classify the image and produce an output which estimates the probability. Let's consider binary classification, whether it is more than 18 or less than 18. So we know that, and in the literature you can find lots of prior works that show that if we let people to have access to this model F here, an internal representation extracted by this model, basically they can infer anything. Like, for example, if there is a sensitive attribute like gender that we don't want to be revealed and we just want age to be classified here. So a machine learning service can extract this if we let them to process our data. Current state is that we can use edge or encrypted computation to hide all the internal computation and just release the output. So in this setting, we can run, for example, the model on the browser or mobile or use encrypted computation and just reveal and just release with the machine learning service provider this single value 93, for example. That is the probability of being more than 18, for example. Now the question is, can a machine learning service just from this 93, 0.93, can they also infer the gender of the data owner or any other sensitive attribute? That's the question that we are answering in this work. That even this single innocent looking number can be manipulated to reveal more than what is supposed to reveal. So in a general setting, we consider that there is a machine learning service providing a classifier F here, and they process our data, and we just let them observe the output of this model in two settings. One where we just release the raw output of the model, or even we can do post-processing and for example, by a softmax option, just reveal the probability-like output, a soft score, as we call it. And so we have such a Markov chain that there is a data like face images, and the service is only supposed to infer y, which is the target, but from the output, the y hat, that is the output of this model, maybe they also trying to infer another sensitive attribute, s hat here. So this is the general setting that we consider. And we show that machine learning models can be trained to be honest but curious, meaning that they can be honest in predicting the target attribute, but at the same time, they can also be curious in revealing a sensitive attribute through this single output. Our main results, which I will talk about them in a few minutes, are that this is because of the over-parameterized property of ML model. Basically, high capacity of ML models allow us to have such an attack. And we show that it is not easy to distinguish between a standard and HPC models. And also we show that if these models are used in a teacher-student or knowledge distillation setting, then there is this risk that a honest but curious teacher can transfer curiosity to students. So to show some results, let me just introduce a brief notation. When I show delta y, I'm talking about the accuracy for the target attribute. Delta s is the accuracy for the sensitive attribute. And a delta y, delta s HPC means that a model which is delta y accurate for the target and also delta s accurate for the sensitive attribute. Let's see this basic example. Consider this synthetic data set, just a binary, two binary attributes, and data is perfectly splitted into 4 regions. And we know that, for example, for predicting y here, we can perfectly use a logistic regression model. But a logistic regression model does not have capacity to be also curious model. This is a relation that we have for a logistic regression between honesty and curiosity. For example, if we use this line, we can just be perfectly honest. We can just predict perfectly y, and we have random guess accuracy for attribute s. But if we choose this decision boundary for logistic regression, then we can have moderate honesty and curiosity, like 70% accuracy, 75%. And if we choose this one, we will be perfectly curious, but no honesty at all. And this shows that a simple logistic regression cannot be at the same time both honest and curious. But if we just double the capacity, like designing a model like this, and we reveal the output by this formula, we can easily see that we can achieve perfect honesty and perfect curiosity. I mean, this model output has just 4 possible outputs, which give us information about both attributes. So the conclusion here is that just by doubling the capacity of a simple logistic regression model, we can build another model that is both honest and both curious in a perfect way for that synthetic data. In the paper, we have more theoretical results on convex optimization, but I cannot explain it here. But how about more complicated data? Let's talk about face images. We have experiment on 2 big data sets of face images. For more complicated, we show that a regularized technique based on entropy can be used to train a model for being both honest and curious. Basically, if you look at this formula, the first one is a simple cross entropy loss function for the target task, but we can add another term to the typical binary cross entropy loss function to encode the sensitive attribute into the output. As we see, for example, when the sensitive attribute is 0, so we can minimize the entropy, and when the sensitive attribute is 1, we can maximize the entropy of output. But this minimization and maximization of entropy can be done by some regularizer in a way that we can again be accurate for the prediction of y. And then by a threshold function, we can easily infer the attribute S, the sensitive attribute, but just by looking at the y hat, which is the output for the target attribute. A result on UTK dataset, for example, for 2 attributes, gender and race, we see that for gender, the standard model can get a very good accuracy. It's the target task, but a standard model cannot be accurate for the race, the top plots. But in the bottom plots, we see that HPC model, just by trading a bit accuracy for the target task, can achieve a very high accuracy also for the race, which is the sensitive task. We also, in the paper, show a more generalized attack for attributes beyond binary attributes. I can talk about this in discussion part. For example, if we consider age and race, 3 classes, each of them, we see that we can train a model that achieves the same honesty or accuracy for the target task similar to the standard model, but can achieve a much higher accuracy in predicting the sensitive attribute. We also considered a compression operation to hide this kind of suspiciousness in this model, because if you look at the average entropy of honest but curious model, you see that they tend to have higher entropy outputs. So this may make them to be revealed by the users. But a compression technique can help to also keep the output entropy of these models as similar as a standard model. And the final result that I'm showing now is a result on a vulnerability to knowledge distillation. And we showed that if a teacher, for example, if this is a typical setting these days, that people who have access to large data sets train a model as teacher and then make them public, and people that have data but don't have label for them use these teachers to do knowledge distillation. And we have shown that this knowledge distillation is susceptible to this kind of attack by the provider of the teacher model. And I think, yeah, that's the basically takeaway of this talk, that machine learning service providers can train their model to encode a sensitive attribute into the innocent looking output for a target attribute. There are some open questions that we can discuss later about how to distinguish between these two, or how to encode more than one attribute, and also the implication of these on other area of machine learning, such as federated learning. Thank you very much.
Okay, thank you very much, Mohammed. Another interesting talk. So we have one more speaker who's escaping me for some reason. which one was next? Sorry, should have. Subham is next. So we have one more speaker in this section, Subham, and then we'll jump into the 30-ish minutes for Q&A. Looks like we'll be slightly less than 30 minutes, but yes, take it away, Subham.
Yeah. Okay. Let's see. Okay. So can everyone see the screen? I think they can. Cool. So hello everyone. I am Shubham Jain, and I am a graduate student at Imperial College London. And today we'll be talking about the ongoing crypto wars, which are based around the messaging platforms that we use, at least I use on a day-to-day basis, like WhatsApp, Signal, and so on. So let's start with the story of when it began. So this started in 2013, when Signal, or then messaging service TechSecure, released an app along with their protocol, which provided two people to chat with each other in a encrypted, end-to-end encrypted fashion, such that the intermediary servers cannot know anything about what they are doing or what they're talking about. In 2014, this protocol was adopted by WhatsApp, then came secret chats in Telegram. In 2016, Messenger by Facebook released secret conversations based on this protocol. And today we have more than 2 billion users who use these end-to-end encrypted services on a day-to-day basis. And Instagram and Messenger might use and adopt end-to-end encryption all over their messaging platforms by 2022. So how does the end-to-end encryption works? And the promise of end-to-end encryption is that when I'm talking to someone, when I'm chatting with someone, it's only me and the other person or the group of people should know what I am talking about, and not the intermediate servers. So how it works is basically, let's say I'm sending a message, there's a shared secret key on my device, which encrypts the message, and encrypted message is then sent to a server. Server then sends this message to the recipient, which then decrypts the shared key, and then we both can share the messages. Now, not just text, we can also send images with this or any other media. And the question comes then, this can also be used to share possibly illegal content. And several organizations and researchers have raised the concern that encrypted messaging platforms can be used to share any illegal content, such as child porn or terrorist content or something else, and illegal as defined by the enforcement authorities. But the server won't know what is going by. And now people came together again to find a solution that, okay, how do we stop this? What do we do? And like in 90s, the first solution that they came up with is key escrow systems, or one of the first. And what it is basically you have a set of devices and the keys are stored on a cloud or in a database in some secured way. And third parties or law enforcement, for example, law enforcement agencies can ask for these keys under exceptional access or under certain circumstances which are predefined. And so these key escrow systems raises significant privacy concerns within the privacy pets community, including by researchers that were there, I think, yesterday and maybe now in the session as well. And the main concern that is being raised against these systems is that, firstly, it is impractical to build such a key escrow system for large-scale data, like you're handling keys for 2 billion users. But at the same time, you need this to be secure and you need this to be abuse resistant. And this concern is grounded in the examples that we have seen over the years. For example, companies like Apple have tried building such a escrow system, but even those have been found to be vulnerable. And the community doesn't have enough confidence that this is possible. So since last few years, people have been wondering that, okay, what are the other possible solutions? And they come up with an alternative, which is client-side scanning. And the way this works is you have now, I want to send a image to someone. I upload it on my app, for example, WhatsApp. Now the WhatsApp will create a digital fingerprint, which is in this fingerprinting algorithm will be part of the app itself. And this fingerprint will then be sent to check for a match against a database of fingerprints of known illegal images. And if a match is found, I wouldn't be allowed to send this message, and some further action will be taken depending on the implementation. And if no match is found, then I can encrypt the data and the message is sent as routine. So again, like when this came out about in last couple of years, and several privacy concerns have been raised against this as well. And firstly, the biggest concern is that this increases attack surfaces. What does it mean? Is that now you have a digital fingerprinting algorithm and a match that is happening, which can possibly be exploited by hackers or attackers or other adversaries. Then the second most important question here is who controls the database? What is the process? What is there in the database? How do you avoid this being abused further? You start with illegal content such as CSAM or child porn. You go with terrorism. What stops them from using it for other purposes? So there is a possibility of mission creep. So based on this, the other concern that has come up is basically, can an adversary evade detection? For example, if I were to send this dog photo, and if a match was found, can an adversary who just has access to this app in a black box setup try to change this image by a little bit and create a new hash such that it will evade detection? And this is the question we ask in our research, is that is client-side scanning is a robust solution? Is it possible to evade detection easily or not? And to do this, we first understand how exactly the proposed client-side scanning will work. And the current proposals rely on perceptual hashing algorithms. So these are standard algorithms that have been there in the usage since a couple of decades, where they are mainly used for efficient image retrieval. The way it works is basically you give an image, it creates an index or a fingerprint, which is much smaller in size. And so it protects privacy in some way. And that's why the claim is that the client-side scanning does not just solve the problem, but it does it in a privacy-preserving way. And the perceptual hashing algorithms are designed such a way that similar images would have similar fingerprints, so that it is harder to modify an image and evade detection, while the different images would have completely different fingerprints. Facebook's PDQ is one of the commonly used open and also open sourced perceptual hashing algorithm. And it is important to note this because perceptual hashing algorithms which are used in practice, a lot of them are closed source and no details are available to the public. So, and the next part is, now you have the fingerprint that you created using perceptual hashing. How do you match the fingerprints? So for each fingerprint, in the database, we match the sent fingerprint with it, and we measure a distance between the two. And this distance is measured using something like a Hamming distance, which is basically you take the two fingerprints and you see how many pixels are different. If number of different pixels is less than some predefined threshold, then you say, yes, it's a match. If there is no such match possible or in the database, you say there is no match found. Now, if it was a safe image or a non-illegal image and a match was found, that is false positive. It shouldn't be there. It shouldn't be flagged. And ideally, it should be said as no match found, which is a true negative. And similarly, we have if an illegal image was found a match, that is true positive. And if illegal image could evade the match, then it will be a false negative. The threshold is basically chosen such that it balances the trade-off between the false positives and false negatives. It is chosen in such a way that both of them are within a certain limit. And what we know is obvious, like as threshold will increase, more images will be flagged, the false positives will increase, true positives will also increase, and the false negatives would decrease. And again, going back to Facebook's PDQ, it recommends a threshold of somewhere from 20 to 90. Why we are mentioning this? Because we'll come back to this later. So what we show is basically now, can an adversary bypass this detection by CSS? And now what we know from our knowledge of the proposed client-side scanning is that our adversary has access to black box, and now it wants to change the image in such a way that the resulting hash is away at a distance of at least t or from the original hash. The adversary will choose the threshold, will choose the image that it wants to perturb, and run the black box attack, or if it is, and see if it is possible. And what we show is basically that more than 99.9% of images can be modified successfully using standard black box adversarial ML techniques for 5 popular hashing algorithms and a wide range of detection thresholds. For this, we used image in a dataset, and we adopted a standard approach for the adversarial attack based on evolutionary strategies. So the images look like something like this. So here on the left, you can see the top examples. You have the original image. On the right, you have the modified image for PDQ algorithm when threshold was 30. At the bottom, you can see for 4 different thresholds for the PDQ that we tried: 30, 70, 85, and 90. And almost all the images seem really very similar. But at the same time, now we know that we can successfully perturb the images. Images look similar, but does it really evade detection? Because now it's not about one image, it's about the whole database. So the question we ask next is pushing hash beyond the threshold t enough to evade detection? And to answer this, we calculate the false negative rate, which is probability that a modified illegal image would evade detection. And we create a data. For this, we use image in the dataset again and a database size of 100,000. And we find that for threshold of 30, 97% of the modified illegal images evaded detection. And this number goes down to 67 as we increase the threshold. So yes, if we increase the threshold, the attack becomes a bit harder to carry out. But is increasing threshold an effective defense? And to measure this, we use false positive rate, which is probability that a safe image is detected falsely or detected wrongly. And what we see is that when we use a smaller threshold, about 1 out of 1,000 images or safe images are falsely detected. But as soon as we go to like threshold of 90, which is where we saw earlier our attack might become a bit difficult. Here, every 3rd image is being flagged wrongly. What does it mean in practice is that if there were 4.5 safe images that were shared daily, 4.5 billion, then almost 1.6 or 1.5 billion images would be flagged daily. So to conclude this, I think there are 3 main points that we discussed today. Firstly, we talked about client-side scanning, which is proposed as a privacy-preserving solution to detect illegal content. Secondly, we showed that CSS is not a robust solution, and almost always an image can be modified to avoid detection, even in a black box setup. That is the proposed way of how it will be implemented. And lastly, we showed that defenses to improve robustness of such systems don't work. We have the paper is available on archive. You can look at it. This work was done in collaboration with my colleagues Anna Maria and Eva Alexandre at Imperial College London. You can follow us on our Twitter. Thank you for that. And this is currently under review. Thank you.
Okay, thank you very much for another interesting talk. So we now have plenty of time for Q&A. I will share my screen again just to put the talks that we just saw back up so you could remember everybody's names and so on to help facilitate the discussion. And please, if you have questions, ask in the chat or be like Ian and hop right up to the mic and just start talking.